Hey there, science fans. Today we're diving into the world of PLCs, or programmable logic controllers. Now that might sound complicated, but trust me, it's not as scary as it sounds. Imagine a small but powerful computer designed specifically to control machines and processes. That's a PLC in a nutshell. These clever devices are like the brains behind countless automated systems we rely on every day. From traffic lights and elevators to amusement park rides and even the machines that make our favorite snacks, PLCs are everywhere. They take simple instructions and turn them into complex actions, making our lives easier and more efficient. Now, you might be wondering what makes a PLC different from your everyday computer. Well, unlike your laptop or smartphone, PLCs are built to survive in harsh industrial environments. They're designed to withstand extreme temperatures, vibrations, and even electrical interference, ensuring they can keep things running smoothly no matter what. PLCs are the unsung heroes of modern industry. They play a crucial role in automating a vast range of tasks, from simple to incredibly complex. Let's take a look at some real-world examples to see how PLCs are making a difference. Imagine a car manufacturing plant. Before PLCs, assembling a car was a highly labor-intensive process. Now, PLCs control robotic arms that weld, paint, and install parts with incredible precision and speed. This not only increases efficiency but also improves worker safety by handling repetitive or dangerous tasks. But it's not just manufacturing where PLCs shine. They're also essential for managing critical infrastructure like water treatment plants. PLCs monitor water quality, regulate chemical levels, and control pumps to ensure safe and reliable water distribution. They work tirelessly behind the scenes, keeping our cities running smoothly. And let's not forget about renewable energy. PLCs are instrumental in maximizing the efficiency of solar and wind power generation. They track the sun's movement to adjust solar panels for optimal energy capture and control wind turbine blades to harness the power of the wind effectively. Now that we've seen PLCs in action, let's pop the hood and explore the key components that make a Siemens PLC tick. Don't worry, we'll keep it simple. First up, we have the CPU, or Central Processing Unit. This is the PLC's brain, responsible for processing instructions and controlling the entire system. Think of it as the conductor of an orchestra, making sure everything works together in harmony. Next, we have the memory. Just like our brains, PLCs need a place to store information. The memory holds the PLC program as well as data from sensors and other devices. It's like the PLC's filing cabinet, keeping everything organized and accessible. No PLC would be complete without input and output modules. These are the PLC's eyes and ears, allowing it to communicate with the outside world. Input modules receive signals from sensors, switches, and buttons, while output modules send commands to motors, actuators, and other devices. Finally, we have the power supply, which provides the electrical juice to keep everything running. Without it, our PLC would be just a lifeless box of electronics. Now, you might be wondering how we actually tell these PLCs what to do. That's where programming comes in. PLCs use a special language called ladder logic, which is a graphical programming language that resembles electrical circuit diagrams. Don't let the name intimidate you. Ladder logic is surprisingly intuitive. It uses symbols called rungs to represent logical operations. Each rung consists of inputs, outputs, and logical functions that determine how the PLC should respond to different conditions. For example, let's say we want to control a motor based on the state of a button. In ladder logic, we would create a rung where the button acts as the input and the motor acts as the output. We can then add logical functions to specify that the motor should only turn on when the button is pressed. Ladder logic allows us to create complex control sequences by connecting multiple rungs together. It's like building a flowchart of instructions that the PLC faithfully follows, making it possible to automate even the most intricate processes.